Welcome to Okonkwo Academy. In this tutorial, I'll be taking you through Norton's theorem. If you are new to this channel, I recommend that you please click on the subscribe button and put us on post notification so that you'll be notified whenever we post videos. Now back to today's tutorial. In this tutorial, I'm going to show you how we will use Norton's theorem to solve for current through a particular resistor. Now, Norton's theorem states that any linear circuit connected between two terminals can be replaced by Norton's current source in parallel with Norton's resistance connected between the same two terminals. Now, suppose we are asked to find the current through this 3 ohm resistor. What we do is that to use the Norton's theorem, we first find the Norton's current, then we find the Norton's resistance, then we draw a Norton's equivalent circuit. We draw a Norton's equivalent circuit which has the Norton's current in parallel with the Norton's resistance, and that too will be in parallel with the circuit that we want to find the current passing through. Now let's move on to the question. So with this, we first find the Norton's current, just like the way we did for the Thevenin. In Thevenin, we found the Thevenin's voltage. I'll put the link to that video for you to go and watch. Now for us to find the Norton's current, we would have to replace through the 3 ohms. We have to replace the 3 ohm by a short circuit. Now we remove the 3 ohm and make it a straight line, where in that straight line the Norton's current will be passing through. So we redraw this circuit. Bear with me as I draw the circuit. So we draw this 12 ohm, then I'm just drawing the circuit. Back to the source. Now I removed this 3 ohm resistor and replaced it by just a short circuit, because Norton's current will be replaced by I will place the 3 ohm by the Norton's current, so this place will be the Norton's current. That's what we are about to find. Then 35 volts, then 6 ohm, 12 ohm. Now the Norton's current is what we are finding. Then this place is 42 volts. Now let's represent here by A, B, C, D, E, F. Now taking a loop, let's suppose a current I flows from this terminal. So a current I flows from this terminal. When it reaches here, it will split. So it splits into I1 and the Norton's current, right? So it splits into I1 and the Norton's current. So we know that I here will be equal to IN plus I1. Now, if you don't understand the reason why we did this, I'll recommend that you go and watch the video on Kirchhoff current law. So this portion is as a result of the splittage of the current at the node. This is a node, so there is a splittage at that current. And since this is the part that we replace by the Norton's current, we say I is equal to I1 plus IN. So I can say that this 12 ohm, the current passing through this 12 ohm is IN plus I1. So taking a loop A, B, E, F, A. So taking the loop in this direction, A, B, E, F, A, we would have, so for us to get the voltage, you know that the current, let's say it starts from here, A, B, E, F, to the negative terminal, then to the positive terminal at last. So we have positive 42, which will be equal to, now we know that the Kirchhoff's voltage law, as it states that the summation of all the voltage source should be equal to the potential drop or the voltage drop across all the resistors. So 12 ohm multiplied by I, right? 12 ohm multiplied by I. Then 6 ohm multiplied by what? I1 plus 6 ohm multiplied by I1. Now the reason why the I and I1 are positive is that they all move in the direction of the loop that we are choosing, right? So if this I moved in the opposite direction, like that one, it will be negative. Or if this I1 moved in the opposite direction, like in this direction or something, like that one would be what? Also negative. But since it is moving in the direction that we've chosen, we would have to use a positive. If you don't understand the sign convention, I will recommend that you go to watch the Kirchhoff voltage law video that we did. So let's represent this by equation 1. Now we can replace this I by In plus I1. So we get 42 is equal to 12 In plus I1 plus 6 I1. So we can get 42 to be equal to 12 In plus 18 I1. So let's represent this by equation 2. Then now taking another loop B, C, D, E, B. So we are taking it in this direction. What? B, C, D, E, B. Now for this part we should be very careful with sign convention. So we are saying B, C, D, E. So it moves from the positive terminal to the negative. So we have negative 35 to be equal to the voltage drop across this. Now we are moving in this direction, so it means that this potential drop will be negative. It will be negative because we are moving in this direction and the current is moving in this direction. The current is moving in this direction. So represented by negative 6 I1. Then you get I1 to be equal to 5.83 ampere. So we get 5.83 ampere. So we can put this I1 into equation 2 to find the Norton's current, right? So you get 42 is equal to 12 multiplying the Norton's current plus 18 times 5.83, right? So we get 42 minus 18 times 5.83 divided by, I'm just making the Norton's current the subject, so divided by 12, which will give you the Norton's current. Now if you punch this, we are going to get negative 5.245. So we are going to get the Norton's current to be negative 5.245 ampere. Now we are done with finding the Norton's current. I said that for you to use the Norton's theorem, you have to find the Norton's current and also the Norton's resistance. The Norton's resistance is found just like the way we did for Thevenin's resistance. So as you already know, for you to find the Thevenin's resistance or the Norton's resistance, they are all the same thing. Use the same way to solve it. You have to deactivate all the sources. What do we mean by a source? A source is like a battery or the voltage sources. So this is a source, this is also a source. So we remove this source and this source, and also the 3 ohm, we replace it by an open circuit which represents the Norton's resistance. So bear with me as I redraw the circuit. So we are going to get something like this. Let me write my 12 ohm, then it will come down. Then for this part, I replace it by an open circuit. Then so this will be the Norton's resistance. Then you have 6 ohm. Then you have 12 ohm. Now the Norton's resistance will be equal to the resultance of these two resistors. Now these two resistors are parallel, and so we write 12 parallel 6, then we find the, so it's going to be 12 times 6 divided by 12 plus 6. Now I've explained why these two are parallel. I said that for two resistors to be parallel, when we traverse through the loop that they are contained in, we shouldn't pass through any source. So when we traverse through this loop as I'm doing, we do not pass through any source. Let me give you another example. So for instance, when we are using this loop, let's say this is just a way to show you how it's done. So let's say if you are using this circuit A, F, E, B, A, because there is, when you traverse through this part, for these two resistors there is a source which is the 42 volt. These two resistors cannot be, they are not in parallel, they are in series, right? Yes. So for this, when we traverse through this loop, we do not pass through any source, and so 12 and 6 are parallel. So we get the resultant resistance to be equal to 4 ohm. So 4 ohm. Now we draw the Norton equivalent circuit, right? As I said, when we finish finding the Norton's current and the Norton resistance, you are almost done with the question. The next thing to do is to draw the Norton's equivalent circuit, and that, to find the current through the 3 ohm, we are going to use current division rule. For the current division rule, to have done a video on it, I will post the link for you to also go and watch if you do not understand that. So the Norton's current, now this is how you draw the Norton's equivalent circuit. So this will be the Norton's resistance. As the law states, then the Norton's current source is parallel to the Norton resistance, right? In the equivalent circuit, this will be the two terminals. Then the resistor that we want to find the current through will be placed there. So that will be the 3 ohm. The Norton's resistance, what do you get? You add 4 ohm. Then the Norton's current, you add negative 5 point or 5.245. Now you can choose to ignore the negative. The negative there implies that the current that we choose, or sorry, the direction that we choose for the current is in the wrong direction. It's supposed to be in the opposite direction. So when we can change the direction that we showed for the Norton's current to be in the opposite direction. So the negative doesn't matter. You can get a positive answer or a negative answer depending on the direction that you choose. So for us to find the current through the 3 ohm, we use current division. So this is the current, the Norton's current that will be moving. Now this current will split at the node, right? So we want to find the current through this resistor. So what we do, I showed you a trick. For you to find the current through the opposite resistor for two resistors in parallel, for you to find the opposite resistor, what you do is that you write the the other resistor, not the resistor that you want to find the current through. So you write the 4 ohm. If you want to find the current through the 3 ohm, you write 4 ohm divided by the summation of the two resistors, sorry, 7 multiplied by the total current, which is 5.245. So let's say if you wanted to find the current through the 4 ohm, that's not what you want to find. Let's say if you wanted to find the current through the 4 ohm, like that one, it will be the 3 divided by the summation of 4 plus 3 multiplied by the total current. But in this case, you want to find the current through the 3 ohm. So the current through the 3 ohm. The current through the 3. So it will be 4 divided by 7 multiplied by the total current. So 4 divided by 7 multiplied by the total current, which is 5.245. So the final answer for the current through the 3 ohm is going to be 2.997 ampere, which is approximately 3 ampere. Sorry, 3 ampere. Thank you for watching this video to the end. Do well to like, comment and subscribe to our channel. Stay tuned for more concepts. Thank you.